We've got an object here that is in between these two dots. Can you tell me what these two dots mean? This one is what? Focal point, yeah. This one is, yeah, we don't want to say center of curvature for the lenses. They would say the second one is the center of curvature for curved mirrors. But for lenses, we just say it's 2 times the focal point. It would correspond to the same distance as the center of curvature for mirrors, but it's not literally the center of a circle like it is for mirrors. Now, having said that, you know what, I should have pointed to these 2 dots as opposed to these 2 dots, because these aren't really the focal point and twice the focal point. It's the same distance, but it's not really the focal point. The focal point is really over here, twice the focal point really over here. The only reason we draw these over here is for spacers, so we know where we've got our object relative to the focal length. This one we've got in between the focal length and twice the focal length. We want to draw 2 rays to determine what the image is going to look like. That first ray is going to go from the top of the object parallel to the principal axis. We draw it to the center of the lens, although it doesn't really go to the center of the lens, right? It goes to the surface, to the boundary of the lens / air, and then it bends, and then when it goes out the lens on the other side, it bends again. But the net effect is the same thing as if it went to the center and then down through the focal point. So it's going to look something like that. Where does that second ray go? By the way, why does that go through the focal point? All rays parallel to the principal axis for this type of lens go through the focal point. That's what happens when we have converging lenses. A converging or convex lens as opposed to a converging or concave mirror. All rays parallel to the principal axis converge at the focal point. All right, where does my second ray go? Top of the object where? Yeah, it's through the optical center, and that's that spot that's literally in the geometric center of the lens. It's going to look something like this. They converge on the right-hand side. You see them converging over here. This is going to produce an image that is, number 1, larger, smaller, same size. Larger. Number 2, it is inverted. And number 3, it's real. It's real because it can be projected onto a screen if we want to. We don't have to. We could look into the lens in order to see this, but we don't have to. We could project it onto a screen if we want to. How do we know that it's real? We can't see it being projected onto a screen right now, so how do we know that it's real? Solid lines intersect. Good. Let's draw our next ray diagram. Refresh your memory on this one. First ray is again going to go parallel down through the focal point. Second ray is going to go down through the optical center. You notice that this time, these 2 rays don't seem to be converging on the right-hand side. So what do we do with those rays? We extend them on the left-hand side. Good. If we draw it properly, we're going to find that they don't converge on the left-hand side either. That means that we have no image, right? Is that it? I'm sorry? Yes, yes. Yes. That I'm not sure. Josiah's question, if you didn't hear it, guys, was, is there a spot, is that the, first of all, is that the type of lens that is used in cameras? And the answer is yes. It's a convex lens that's used in cameras. Is there a spot where you wouldn't be able to see the image? Yes. Any camera lens is only good to a certain distance. If you get too close, it's not good beyond that. So basically, it's not good beyond focal length, right? If you're inside the focal length, it doesn't work out. The reason is at the focal length it produces no image. Inside the focal length it produces a virtual image. And if we want to produce an image onto a screen, on the old style cameras onto a piece of film, right? Or on newer cameras, obviously, onto a digital collector, a CCD it's called, then we have to have a real image produced. So inside that focal length it doesn't work, including at the focal length. It doesn't work. The secondary question to that, the follow-up question to that was, is that what they talk about when they talk about a blind spot for a security camera? I would assume so, but I can't really say that for sure. I'm not real familiar with that, but I would assume that that's what they mean by talking about a blind spot with a security camera. Certainly at the focal length, they wouldn't be able to see anything. And inside the focal length, you're going to produce a virtual image, which you wouldn't be able to see anything either. I would suspect that the focal length of that, the lens on that camera would be fairly small, relatively small, which would mean that, you'd have to be really close to the camera in order to be in that blind spot. But I think that's what it would be. Yes. Yep. I'm sorry. Is a converging mirror a magnifying glass? No, no. Because a magnifying glass would have to be a lens. Although you can magnify with a converging mirror, it's just not very practical sometimes. Depends on the circumstances. Yeah, that's a converging lens. Now, that would work as a magnifying glass, but not when the object is at the focal point. So, yes, a converging lens can be a magnifying glass, but not every time. Depends upon where the object is placed. Basically, in order to make it work as a magnifying glass, you have to have the object closer than the focal length. So in other words, our next ray diagram right here, we have our object inside the focal length. That will serve as a magnifying glass. And that's going to end up producing a virtual, upright, larger image. Let's do that here in just a second. First ray, parallel, down through the focal point. Second ray down through the optical center. Doesn't converge on the right-hand side. Let's extend them. Does converge back here on the left-hand side. So again, you can see that it is 1, larger, 2, upright, and 3, it's virtual. That's exactly what you see when you have that magnifying glass, right? Whereas you have to look into the lens to see it. Okay, when you do look into the lens, you see a bigger, upright, virtual image. And you have to have the object that you're looking at through the magnifying glass fairly close to the magnifying glass. In other words, if the focal length of the magnifying glass is 10 centimeters, the object that you're looking at has to be smaller than 10 centimeters from the lens. Okay, so Josiah is talking about, a blind spot in a security camera. You don't want to have the object within that 10 centimeters, right? But for the magnifying glass, you do. Well, the whole point of it's different, though, right? For a security camera, you want to produce a real image on a screen inside the camera. For a magnifying glass, you want to produce a virtual image that's right side up that you can physically look into the lens to see. The same lens, but used in 2 different contexts. All right, we took a look at this one on Friday as well. I asked you to draw some more ray diagrams for this one. I think you would have found that they were all the same, or at least all pretty much the same. First ray parallel to the principal axis. Where did it go from there? Didn't go down through the focal point. It went away from the focal point. If we extended this line, it would go right down through the focal point. And we'll wait on doing that, though. Second ray is going to go down through the optical center. And just the same as for the last set of lenses, it's going to keep going. If we extend this one back, you see a couple rays converging there. Technically, you don't actually yet. Technically, we don't have 2 rays converging yet. We have to extend this one backwards. Now we see 2 dotted lines intersecting right here. Now, the reality is, we don't actually need to draw that second dotted line because we know where it goes, right? We know that we're going to get 2 lines converging at the spot where I have the red arrow drawn right here. But technically, it should be another green dotted line going backwards. If we have 2 green dotted lines going backwards, intersecting with each other, we know that it's a virtual image. You got to look into the lens in order to see it. We also can tell by the picture that we see here that it's smaller, and we can see that it's upright. You guys draw the other 4 diagrams? Did you find you get the same characteristics for all 5 of them? Yeah. You would have found that the exact position of the image would have changed a little bit. You would have found that the exact size of the image would have changed a little bit. I think it would have gotten bigger, I believe, right? But you still would have found that it was, for all 5 diagrams, smaller than the object was, and upright and virtual for all 5 cases. Is there any questions with any of those diagrams on this? Those ones? You want to go over another one, or are we okay with those? All right. This, I got to tell you, this page that you see up on the board right now was my favorite. I mean, it's all relative. It was my favorite page of notes to create for all of Physics 3rd. This page that you see right here. Why? It is exactly the same as a page of notes that you saw earlier, except this word was changed. So literally all I had to do is click copy, click paste, change the word mirror to lens. It's exactly the same page, and in fact, the stuff that I'm going to write on it is exactly the same. There are two equations that we use to analyze curved lenses, just as there were for curved mirrors. Those equations for curved mirrors were the mirror equation, 1 over f is equal to 1 over do plus 1 over di. Well, now we're going to call it the lens equation. 1 over f is equal to 1 over do plus 1 over di. Same equation, though. Works the same way. Second one, the magnification equation. hi over ho equals negative di over do. F is the focal length, still. Do is the object distance, still. Di is the image distance, still. Hi, ho, m, the image height, the object height, and the magnification, still. Units can be centimeters, meters, kilometers, inches, miles, light years. Doesn't really matter, as long as it represents a distance and as long as you're consistent. It will be positive sometimes, and they'll be negative sometimes. When are we going to find that focal length is positive? Well, we'll find that the focal length is positive when it's a real focal point. It's negative when it's a virtual focal point. Now, for lenses, things are a little bit different than for mirrors when we're talking about the focal point. When did we have a real focal point with mirrors? What kind of mirror was it that gave me a real focal point when we had mirrors? A converging mirror. Well, it's the same thing for lenses. You have a real focal point when you have a converging lens. But for mirrors, a converging mirror was a concave mirror. A converging lens is a convex lens. So we're going to say converging or convex. A converging lens or a convex lens. A virtual focal point or a negative focal length will be a diverging lens or a concave lens. So the same basic fundamental answer applies here for lenses as it does for mirrors. If you have a converging lens or a converging mirror, it's a positive focal length. But a converging lens is convex, a converging mirror is concave. So we got to keep straight the difference there. That's the only difference, but it's an important one. DO. Now DO is the object distance, and it's going to be positive when you have a real object. And it's going to be negative when you have a virtual object. You tell me when you're going to have a real object? For us, the object is always going to be real. It's not true all of the time. There are situations when you can have a virtual object, but that's not going to happen for us in physics 30 because you need a couple lenses in the system to make that happen. We don't have to do that. What about DI? You can cheat here, right? You guys can look back at your chart that you did for your mirrors, and it's the exact same things we're going to fill in here. DI is positive when you have a real image. And DI is negative when you have a virtual image. When do you have a real image? Well, sometimes you have a real image for a convex lens or a converging lens, but not always. When do you have a virtual image? Sometimes it's a virtual image for convex lenses. It's always a virtual image for concave lenses. What about HI, HO, and M? The green ones here are all positive if they're real. The blue ones are positive if they're, what is it? Nope. They're not virtual. The blue ones are positive if they're upright. Good. If you have an upright image, then we're going to say that HI is positive. If you have an inverted image, then we're going to say HI is negative. HO is going to be positive if the object is upright, which is 95% of the time. And it's going to be negative if you have an inverted object, which isn't very common but could happen. And finally, the magnification, M, just the same as it was for mirrors, M is positive. Well, usually, if the image is right side up, then M is going to be positive. But if the object was actually inverted, which doesn't happen very often, then the image would have to be upside down or inverted in order to produce a positive image, or positive magnification. So M we're going to say is positive if the object and the image are on the same side of the principal axis. If the object is right side up and the image is right side up, M is positive. If the image is upside down and the object is upside down, then we're going to say that the magnification is positive as well. If it's negative, well, you got to have one of them right side up, one of them upside down. It doesn't really matter which one is which, but they got to be flipped over relative to one another. Principal axis, yes. PA is principal axis. This should seem familiar to you. Whether you remember all of these things or not at this point, that's not sure if you're going to remember it at this point, but it should be familiar to you because you've seen this almost the exact same page before. The only difference between this page and the page that you wrote down last week is number one, the word lens. Last week it said mirror. And number two, a real focal point was produced for a converging mirror, just the same as it was for lens, but that converging mirror wasn't convex, it was concave. And the diverging mirror wasn't concave, it was convex. So those three things that you see circled in red there, the only difference, everything else should be word for word, letter for letter, exactly the same as it was. Now, when we solve problems involving mirrors, I suggested to you that you either highlighted or underlined or circled in red or something, drew attention to the type of mirror that you had, right? You read the question, it says a convex mirror or a concave mirror. Circle it and write down the focal length is either positive or negative. I'm suggesting you do that even more than ever because now you're not only trying to keep straight convex and concave, now you're trying to keep straight mirror and lens. So there's a whole bunch of possibilities now, right? Convex mirror, concave mirror, convex lens, concave lens. Okay, really, really draw attention to that now. Okay, if you think people made mistakes on it before with positives and negatives, okay, that doubles now the mistakes that are made. If a quarter of you were going to make the mistake before, now half of you are going to make the mistake, unless you draw attention to that. Okay, let's take a look at 13.7 on 681 here. It says a 2.5 centimeter high object is placed 10 centimeters from a diverging lens. Diverging lens. Doesn't really matter at this point whether it's a lens or a mirror. If it's diverging, it's going to give you a negative focal length. Now, if they said concave lens, that becomes a little bit trickier. Because then we got to say, okay, concave. Well, sometimes that's a real focal point. Sometimes that's a virtual focal point. Depends on whether it's a lens or a mirror. Right, Dane? Concave lens, we would have looked at and said, okay, it's a lens. Concave lens is diverging. Since it's diverging, we're going to make it a negative focal length. Determine the image distance, the image height, and the attributes or the characteristics using the thin lens equation. That's going to be HO. We're going to assume that's positive because it doesn't say, but we'll assume upright. Placed 10 centimeters away, that's going to be DO. The focal length is 5. We're going to make that negative 5. And I'm going to write that down right now, right with it. We're going to determine the image distance, DI, the image height, HI, and we want to find the attributes or the characteristics, which we'll worry about after we've calculated the two things that we're looking for. We're not going to draw the ray diagram here because we've already drawn all 10 possibilities. You can go ahead and do that again as review if you want, but you've done it. As long as you understand the diagrams we drew, you should be okay for that. Okay, let's see what we can do here. We want to find DI, let's say 1 over F. is equal to 1 over dO plus 1 over di. The focal length is -5. So let's write that down, 1 over -5. 1 over the object distance is 10 plus 1 over di. Okay, we've done this a bunch of times now with our calculators. We know exactly what we're doing here at this point. We're going to say -5 x to the minus 1. We're going to subtract from that 10 x to the minus 1, right? 1 over -5 minus 1 over 10. Get an answer for that? It doesn't give us di, it gives us 1 over di. Let's flip that over, though, by pressing x to the minus 1 again. We get -3.333. That's my unrounded number, just in case I need to use that again. My rounded number would be -3.3 centimeters. A simple thing like forgetting to put that negative in there for the 5 centimeter focal length, what's it going to do to us? Now, let's check. Shouldn't matter that much, right? 5x to the minus 1, subtract 10x to the minus 1 gives us 0.1. We flip that over, and we get an answer of 10. So if you do it correctly, by putting in the negative there, you get -3.3. If you do it wrong, by not putting in the negative, you get 10. Those are two completely different answers. That's why we got to be really careful to put that in. Okay, looking for HI. Let's say that HI over HO equals -di over DO. HI over 2.5 equals -3.333. Is that right? What's wrong? It should be -3.3. Good. Over DO, which is 10 centimeters here. So how are we going to do this one? On our calculators, we'll say 3.333, and it's positive now, right? Because a negative is a positive. Let's multiply that by 2.5. Let's divide that by 10. And for that, we should get an image height of positive 0.83 centimeters. Okay, what about the attributes now? Is it larger, smaller, or is it the same size without drawing a ray diagram? Smaller. The object height was 2.5. The image height is 0.83. It's gotten smaller. Is it upright or is it inverted? It's upright. How do you know that? HI is a positive value. It's got to be upright. Good. Is it real or virtual? How do you know it's virtual? That's correct, by the way, but how do you know? Sorry? No. F is negative, tells me that it's a virtual focal point. DI is negative. Good. Okay. Negative for F, DI, and DO means virtual, but negative for F means not a negative image. It means a negative focal point. Although having said that, for diverging lenses, you always end up getting a negative DI, always. So that would work, I guess, in that case. Is that okay? If you were kind of just starting to become comfortable with mirrors when we moved on and said, oh man, I wish we were just doing a little bit more mirror stuff because I was kind of becoming okay at it. You know, I think with a few more problems, I could become really good at it. Well, basically, here you go. Okay, we're dealing with lenses now, but they're really the same problems, exactly the same thought process. The only thing is you got to remember the ray diagram's a little bit different. Sometimes you get a virtual image when you got a real image for mirrors, and the focal lengths. That's what you got to be really careful with, is the focal lengths. When is it positive? When is it negative? Okay, otherwise, exactly the same. Take a look at page 681, please. You only got 3 of these questions. Did with mirrors, we had 5 practice questions. I guess they figure you're getting better at these by now. Okay, see what you can do with those 3 questions over the next 10 minutes, please. Okay, I'm going to ask you to finish up these 3 questions for homework, please, but I'm also going to ask you to do questions on page 603, numbers 1 to 2, 4 to 5, and we'll go 7 to 14, please.
Yeah, nurse to the front office, please.
1 to 2, 4 to 5, 7 to 14. Okay, that's it for today. Have a good night, everyone, and we'll see you tomorrow.